Okay, here is the warm-up for lesson 4.11. 4.11 is a review of the content for Unit 4. But before we dive into that, let's go ahead and talk about this warm-up problem. And it's dealing with all those relationships that we've been working through the last few days, last few lessons here. And one thing I want to emphasize on this particular problem is that this is the graph of f prime, and all of those questions are asking about f. So we need to make sure that we are taking those questions in f and translating them into the graph of f prime, okay? So we don't want to make mistakes. We don't want to say f is concave up when this graph is concave up, because this is f prime, it's not f, okay? So let's go ahead and go through each one of these questions. One other thing I wanted to note is that I wanted to make this a closed interval. So at the endpoints -2 and 11, we have closed intervals because that will help us understand a little bit more about extrema as we go along. So number one, it says, over what interval is f decreasing? So number one is pretty easy. We want to justify what we're looking for. F is decreasing when, well, thinking of the chart that we have, f is decreasing when f prime is negative, when f prime is negative. Okay, so we would conclude that f prime is negative from -4 less than or equal to x less than or equal to 11. So that's our answer for number one. And again, in the past, we've talked about technically f prime is not negative when x equals 6. F prime is 0 there. So a better way to justify this might be to say f is decreasing when f prime is less than or equal to 0. So that, but anyways, that's the question. That's the answer for number one. Number two, it says, at what x values does f have a local max or a local minimum? Well, we would say this: f has a local maximum when, and again, let's look for justification. F has a local maximum when f changes from increasing to decreasing, or interpreting that in light of f prime, f changes from increasing to decreasing when f prime changes from positive to negative. So we'd say that we have a local maximum when f prime changes from positive to negative, which would imply when x equals -4, okay? And then f has a local minimum the other way. F has a local minimum when f prime changes from negative to positive. Well, f prime doesn't change from negative to positive anywhere in this graph, so there is no local minimum in that regard. But now I want to look at endpoints here. We always want to consider all our critical points when we're talking about extrema. Critical points are when f prime equals 0. We've addressed those. Well, actually, we didn't address when x equals 6. But because f prime does not change signs, f does not change direction. So there is no extreme at x equals 6, since f prime does not change signs when x equals 6. But at endpoints are another set of critical points. So we want to interpret this here, and I'm going to draw a little graph here, a little idea. When x equals -10, we don't know what f actually is, but we can see all the values to the right of x equals -10. We can see that f prime is positive, which implies that f is increasing. And that's a good way to see it, observe what's happening here. Since f prime is positive over this interval, f is increasing over that interval. Well, if f is increasing, that implies that this endpoint is a relative minimum. So let's go ahead and justify that. That's going to take a little bit of work here. We would say that f has a local minimum when x equals -10, since f prime of x is greater than 0 for -10 is less than x is less than -4. So since f prime is positive over the interval just to the right of -10, f prime is positive there. That means f is increasing. Well, if f is increasing, that means that endpoint is going to be a relative minimum. Now let's look at the other end here. when x equals 11. So I'm going to do the same type of thing. Here is the endpoint 11. And if we're looking at f prime, we can see that f prime is actually negative for the interval from 6 to 11, which implies that f is decreasing over that same interval. Since f is decreasing to that endpoint is also a minimum. It's a local minimum because it's lower than all the points around it. So we can justify that as well. We can say that f has a local minimum when x equals 11, since f prime of x is less than 0 for the interval immediately preceding that endpoint. So for 6 is less than x is less than 11. Okay, so that's identified all our local extrema, our local maximums and our local minimums. Okay, so for number 3, I'm going to go ahead and erase number 1 here. For number 3, we're looking for points of inflection. So let's go ahead and justify points of inflection. Well, number 3, f has a point of inflection, at, or when, now let's interpret this here. F has a point of inflection, that's the last line in our chart. F has a point of inflection when f changes concavity. We're not looking at f, we're looking at f prime. So f has a point of inflection when f double prime changes signs, which implies that f prime changes direction. Okay? So f has a point of inflection when f prime changes direction. Now I want to be clear when I say changes direction. I don't want to just say changes direction, because changing direction in math can mean an infinite set of things. It could mean changes direction from going to the right or going to the left. It could mean changes direction from going up to going down. It could mean changes direction from going in to going out. There could be a lot of interpretations for changing direction. So we want to be specific here. F prime changes direction on a coordinate plane when it changes from increasing to decreasing or decreasing to increasing. So we would say f has a point of inflection when x equals -7 and 6, -7 and 6, since f prime changes from increasing to decreasing. Okay, since f prime is changing from increasing to decreasing at those 2 points, we have a point of inflection on f, and we can go through that whole justification, because when f prime is changing from increasing to decreasing, f double prime is changing from positive to negative. If f double prime is changing from positive to negative, f is changing from concave up to concave down. And then we can also say f has a point of inflection when x equals 0, since f prime changes from decreasing to increasing. Okay, so from decreasing to increasing, we also have another point of inflection for the graph of f. Obviously, it's not a point of inflection for this graph because we don't see a change in concavity. We're looking for change in concavity of f. All right, so that's number 3. And then the last one, number 4, is pretty easy based on what we just talked about. 4 is asking for when f is concave up. So f is concave up when f double prime is positive, but we're not looking at f double prime. So we'd say f is concave up when, if you want to write it out, when f double prime is positive, but we're not looking at f double prime, we're looking at f prime, so we need to interpret it that way. Therefore, f double prime is positive when f prime is increasing. So where is f prime increasing? F prime is increasing from negative 10 less than x less than negative 7, and 0 is less than x is less than 6. So that is our answer for number 4. So I hope that warms you up to a whole bunch of review problems coming up here pretty quick. But stick around and see how a lot of what we've been talking about, it relates to a lot of good practice AP questions.